Okay, he obviously had technical problems, but this talk is also going to be about taking things to the bleeding edge and pushing the limits. And Muhammad tried to measure signals of, I think, a USRP, a B205 mini with a very sophisticated measuring device. So, dear video team, please play the contribution.
Hi everyone, thank you for joining my talk. My name is Muhammad Ismail, a PhD scholar from Loughborough University, UK. Today I will be presenting our work on a high precision pulse characterization using software defined radios, specifically the USRP B205mini-i, and how we have employed ultra-fast serial data acquisition technique to analyze key pulse properties. So this presentation is divided into 6 key sections. I will begin with the introduction to the topic, followed by our research objectives. Then I will explain the methodology, go through the results we obtain, and finally conclude with the key findings. So first to the introduction of the topic. So in recent years, software-defined radios or SDR have become essential tools for building flexible, low-cost, and scalable communications and sensing systems. Among these, the USRP series by Atos Research is widely used due to its modular design and compatibility with the open source GNU radio software. Our focus is on the USRP B205mini-i, a cost-effective device which supports full duplex communication from 70 megahertz up to 6 gigahertz with a bandwidth of 56 megahertz. Accurate pulse characterization, including the measurement of rise time, pulse width, and jitter, plays a crucial role in radar, wireless communication, and timing systems, where a high signal fidelity is essential for reliable communication performance. This study investigates whether we can achieve a sub-nanosecond precision using the B205mini-i while using ultra-fast sampling oscilloscope as a receiving device. Our aim is to demonstrate even low-cost SDR can meet the precision demand of the modern system. In pulse-based communication, we often analyze signal in both the time and frequency domains. In the time domain, parameters such as pulse width, rise time, and jitter affect how precisely we can detect or locate a signal. For example, a faster rise time means we can identify signal edges more clearly, while low jitter result in more consistent timings. In the frequency domain, bandwidth and spectral shape defines how the signal behaves in terms of range and efficiency, which leads to improved smoothness of and fidelity of its temporal shape. There is a very limited data on how well a compact, low-cost device like the USRP B205mini-i performs in detailed pulse characterization using a high-speed serial data acquisition. So the main objective of our research are given over here. My apology for that, all are given as 111, but they should be considered as 1, 2, 3. So the first objective is to develop a high precision methodology for characterizing pulse using SDRs. extract the key pulse parameter like rise time, jitter, and amplitude via post-processing. Evaluate whether affordable SDR hardware like the USRP B205mini-i is viable for a high accuracy use cases such as radar and pulse communication. So this is the methodology section of our research, which I will explain a bit. So we use GNU Redo open source application to generate a pulse. That pulse is modulated for 2.4 gigahertz frequency using USRP B205mini-i. To safely capture this signal, we attenuate it by a 30 dB before passing it to a high-speed oscilloscope, which is a LeCroy SDA'25, which is capable of sampling any signal at the sampling rate of 18 giga samples per second, which is a picosecond precision. Finally, the captured waveform is post-processed in MATLAB to extract the signal parameters. So we have tested a range of pulse width from 10 microsecond to 25 nanosecond. But due to the presentation and time constraint, I will only present over here the 10 microsecond results, because it's quite an extensive work because we have done the work from 10 microsecond up till 25 nanosecond at a very diverse sort of a receiver and transmitter sampling rates. So that's why we'll only present the result of a 10 microsecond pulse. During this experiment, the transmitter sampling rate was kept constant of 10 million samples per second, while the receiver sampling rate was varied accordingly from 100 million per second, 100 million samples per second to 10 giga samples per second. The oscilloscope captured these variation, allowing us to study how sampling rate affect signal fidelity. So to analyze the signal, we have defined an evaluation matrix. So we categorize the matrix into three different categories, like time domain. In time domain, we have considered the rise time, jitter, and pulse width. Pulse width is essentially is fixed from our side, but we have to analyze the rise time and jitter. Power matrix is mean and instantaneous power of the signal, and spectral and noise properties. So bandwidth and signal to noise ratio. These metrics provide a comprehensive understanding of the pulse characteristic under different configuration. So we are coming towards the result. So in result, first we are considering the rise time of the pulse. So we started the experiment with our 10 microsecond pulse at the transmitter side. Like USRP was configured to a 10 megasample per second. And at the receiving side, we use the sampling rate of 100 megasample per second. As we increase the receiving sample rate, rise time significantly improved. Like at the 100 megasample per second, the rise time was 790 nanosecond, which was improved to 132 nanosecond at a rate of 250 megasample per second. And even above 250 megasample, we use 1 giga samples and 10 giga samples as well. which improve further the rise time up to 111 nanoseconds, which where the ideal rise time for a single pulse, a single sample at a 10 megasample is 100 nanoseconds. So this is the graph which shows this graph, which is the first one. Here the sampling rate at the transmitter is 10 megasamples per second, while the receiver it's 100 megasample per second. Although it's 10 times higher than the transmitter sampling rate, still the rise time is not really very good. Like the rise time it shows is 790 nanosecond, which is a lot. When we increase the sampling rate at the receiver up to 250 megasample per second, the sampling rate reduced from 790 nanosecond to 312 nanosecond, which is shown in the figure B. Upon increasing the sampling rate much more higher as compared to the transmitter side, like increasing the bandwidth of the receiving device, which is 1 gigasamples per second, the rise time reduced to 143 nanosecond. That is a huge improvement. And when we increase further the sampling rate from 1 gigasample to 10 gigasamples, the rise time is 111 nanoseconds, which is very much near to the ideal rise time, which is 100 nanoseconds mathematically. Now we come towards the jitter. Or jitter measures the variability in pulse edge timing. So how jitter effect is affected, or how it is like measured. So as the receiver sampling rate increased, jitter reduced significantly. Like the sampling rate at the receiver side, again, we increased from 100 megasample to 250 megasamples, and then 1 gigasamples, and then 10 gigasamples. So averaging multiple signal revealed consistent waveforms and at ultra high receiver sampling rate. Jitter was nearly negligible, confirming that the precision of the pulse alignment. So here's the result for the jitter analysis of the pulse. The line in black shows the mean signal, which is taken for multiple pulses of the sequence. So the first figure A, where the transmitter sampling rate is 10 megasample, while the receiver sampling rate is 100 megasample per second, it has a quite wide jitter. As this whole edge is quite widely, is broadened. But when we increase the sampling rate at the receiver side, the bandwidth of the receiving device, still there is a jitter, but the jitter has reduced almost half of in the first case. But in the case of the 1 gigasamples per second, the jitter has improved a lot, where all the sequences are lying on the mean sequence. And in case of 10 gigasamples per second at the receiving side, like at the receiver device, we can see that the jitter is almost zero, because the mean sequence and all the sequences are aligned to each other. These figures were drawn in such a way that all the sequences or all the pulses were plotted upon each other, just to make sure that how these pulses are deviated from each other. And the mean sequence was calculated just to see how how the other pulses or the jitter is uh, moved or it's broadenedly like so widely wide from the mean signal. So now over here we can say that by increasing the number of samples at the receiving side, we can say that the uh, receiver device, increasing the bandwidth of the receiver device, the jitter can be decreased significantly. Now we see the filtering effect. The filtering effect was filters were used just to check whether the mean sequence, it will be affected by the applying FIR high pass filter. So we use a high pass FIR filter, and the reason for that was that if we see these figure from the previous jitter analysis, we see that the mean signal, or here in the fourth diagram, the mean signal has quite a bigger distortion at the steady state area, while it has a very low jitter, but still at this area, which is quite wide as compared to the previous cases. So to minimize this noise was effectively produced by the a very high sampling rate due to the system. It is actually the system noise due to the very high sampling rate. So we use sampling to see whether, we use the filtering to see whether the noise can be removed and how can it affect the jitter and rise time. So we came to a result that at a very low sampling rate, the signal were distorted quite uh, on a large scale. Like if I show you the graph, this is the graph after applying filter to the mean sequence. The signal in purple is actually the mean signal, and the other three signal, the FIR filter with different coefficients are applied over here. So these signal are deviated, and the jitter rise time, they all have been distorted by applying filters. But this distortion is reduced at a higher sampling rate, and at a very high sampling rate at 1 gigasamples and 10 gigasamples, they reduce the system noise and smoothen the steady state area of the pulse. So we can say that at a higher, very higher sampling rate, we can use the filter, but at a low sampling rate, I mean at 100 megasamples and 250 megasamples, filtering was not very useful. So now come to the analysis of the sampling ratio and the noise features. The sampling ratio means that how much sampling ratio we can, what's the sampling rate at the DX side and what's the sampling rate at the RX side. So through the experimentation, we have kept a minimum of 10 sampling ratio. Like at the transmitter, we use 10 megasamples, and the minimum sampling ratio at the receiver we use is 100 megasamples per second. So we concluded that for a very good timing and jitter analysis, we use the 10 sampling ratio. Lower sampling ratio leads to a poor edge representation and increased jitter. While ultra high sampling at the receiver side captures more noise because the system produces a lot of noise due to very high sampling rate, degrading the signal clarity and offsetting the temporal resolution benefits. Let's suppose if we use a very high sampling rate, So there are sort of a noise is introduced on the steady state area of the mean pulse, which is like not very useful if we use a very ultra high sampling at the receiver side. So averaging and filtering are essential post-processing strategy, and they effectively suppress the noise. So we found that the sampling ratio of at least 10:1 between the receiver and transmitter gave optimal results. Balancing fidelity and noise. Increase sampling rate improves resolution, but may degrade the signal to noise ratio, necessitating the averaging and filtering as compensation. So this is the conclusion. So to summarize, I can say that the higher sampling rate at the receiver side improved write time and jitter, but introduce noise at the steady state area of the pulse. Beyond 1 gigasample per second, benefits are minimal due to hardware limitation and noise, because if you're using ultra high sampling rate, the hardware produces a lot of noise due to the system components. So a 10:1 sampling ratio is ideal if we are doing a pulse characterization for any of the device. And filtering and averaging are essential to maintain signal clarity at a very high sampling rate. So at a very high sampling rate, we can use the filtering, like we can use FIR filter, but at the low sampling rate, like 100 samples per megasamples per second and 250 megasamples per second, FIR filter were not that useful. So this is the conclusion. So thank you for being with me and for your attention. I welcome any question or feedback.
Okay, hello, Muhammad. Thanks for
Hello,
coming in.
yeah.
In the beginning,
Actually,
yes,
due to the time issue, UK and Germany time, so that's why I forgot.
yeah, well, there are occasional technical problems, yeah. So, are there any questions? No questions. Well, so your talk obviously was very, very explanatory. So the audience does not have any questions. Okay.
Oh, thank you.
Nevertheless, Mohammed, thank you for your contribution, and thanks for sharing your measurements. This SDRA today had a lot of talks about pushing the boundaries, going into details, maxing out values, and seeking, well, trying to reach performances as far as possible. And yeah, well, so thanks a lot. Thanks very much.
Thank you.
And well, hope to see you soon. Thank you very much.
See you.
Thank you very much. Thank you.
Thank you. Thank you.